up until this point, we've been looking at chemical equations and really working under a series of assumptions in our calculations. We have our stoichiometry, our balanced chemical equation, and in our calculations, the assumption is that given oxygen, there will be enough of the reagents to completely react to form CO2 and water in this particular example. So those are the assumptions, that there is enough of each compound and the reaction works completely. Let's take a look at the case where the real world starts to intrude and we end up with situations where initially the first thing we're going to talk about is reactions do not run to completion. So let's focus on this example where reactions do not proceed completely. For this, we introduce two new concepts. One is the theoretical yield. The theoretical yield is if this reaction was run under the conditions given, it would proceed with 100% efficiency to produce the answer that we are curious about. In other words, it's what we've been doing for the past 2-3 weeks. So, given our 3 grams of lithium, I produce 5.02 grams of lithium nitride. The assumption is that all of the lithium is converted into lithium nitride. Now, this may not be the case in reality. This reaction could have side products that chew up the lithium, consume the lithium to make other things. And in those cases, the amount of lithium nitride that is produced would be significantly degraded. So if we assume that all of the lithium is converted to lithium nitride, we have a number that we call our theoretical yield. The theoretical yield is the amount of material formed under perfect conditions. So in this case, 3 grams of lithium going to 5.02 grams of lithium nitride, the 5.02 grams would also be our theoretical yield. We basically answer the problem like we're determining the amount of product. And usually theoretical yield is geared towards the product. Now theoretical yield is usually expressed as grams, but in certain cases you can express it as moles. Usually you're comparing it to something else. And so if your boss says how much you're going to make, he wants to know how many kilograms are coming out at the end. So that's the concept of theoretical yield. Actual yield, as the name implies, is what you actually obtain. This number is something that is given to you or one that you go out and measure. So in a problem, it would show up as the actual yield of the problem, or you only make X number of grams. That's the actual yield. You can obtain something called the percent yield by taking the actual yield, dividing it by the theoretical yield to give you times 100 to give you percent yield. So let's go back to our lithium nitride example. The theoretical yield was 5.02 grams of lithium nitride. If you only produced 1.3 grams of lithium nitride, this would represent your actual yield, and this would represent your theoretical yield. Again, we're told these numbers, at least the actual yield. The actual yield you're usually told or determined in the problem in some fashion. In the lab, you physically go out and weigh it. You scrape out your container and you shake out the last bits and you weigh it to see how much you actually made. In this case, though, we're told it's 1.3, and so we can say that our percent yield for the reaction is 25.9%. Take our actual yield divided by our theoretical yield, we get to 25.9%. So that's how we would calculate it. A more complex example would be as follows. You take a 1 gram sample of sugar and you combust it in oxygen to produce 1.0 grams of CO2. Determine the percent yield. So if we want to determine the percent yield, we're going to need an actual yield and a theoretical yield. Well, the actual yield comes from the problem. Say 1.209 grams, 1.20 grams. So that's our actual yield, grams of CO2. Now what we need is a theoretical yield. Well, to get the theoretical yield, all we have to do is pretend like the product goes to completion. Find out the predicted amount of CO2. Now, luckily for us, that's easy. We know how to do this. We take our grams of sugar, I'm just going to write it as sugar, convert it into moles of sugar, and then we take those moles of sugar and convert it into moles of CO2, and then into grams of CO2. We can set that up relatively quickly. Grams of sugar. We can obtain these values from the molecular weight of sugar. This is from the equation, and this is from the molecular weight of CO2, which happens to be 44 AMU. 180.2 grams of sugar, that is equivalent to 1 mole of sugar. And for every 1 mole of sugar, again, these numbers come straight from our equation. 1 mole of sugar requires 6 moles of CO2. And then from 1 mole of CO2 is equivalent to 44 grams of CO2. And then a little calculator magic says that 1.46 grams of CO2 will be produced.
Yay! No! Answer the problem.
All right. The problem wasn't asking you for how many grams of CO2. The problem was asking you the percent yield. See, I see it all the time. It's like it's so exciting to get the answer that you sort of forget that that's the answer before the answer. Right? We often need the answer, the problem, before the problem. The real answer is our actual yield, 1.20 grams of CO2, and divided by our theoretical yield, 1.46 grams of CO2, times 100, to give us a percent, or 82.2%. So, percent yield is something that you can determine given an actual yield. But it's also usable in a different way. And that is, given a percent yield, you can also predict loss or breakage or how much real material you need to make. The example I like is cookies. I got 2 little boys at home. If I want to take a dozen cookies to the school bake sale, so I want 12 cookies, I know that for every 4 cookies, I know that for every 4 cookies I make, one of them is going to get eaten by the kids. All right? So I have a 75% yield. 3 of them actually make it. 1 of them ends up in one of my boys' belly, or my belly for that matter. So if I want 12 cookies, I need to start with 16. How do I know? Yield can be expressed as actual over theoretical. So we can also express it as 0.75 over 1 or 75 over 100, depending on how we look at it. That's the actual yield over the theoretical yield. And we can use that fraction as a way of expressing how much we need. 12 cookies, that's the actual yield. So if I want these 12 cookies, I know that I will need 75 cookies for every 100 cookies. That says I need to cook 16 cookies. Now, the other way to do this is to divide this number, your actual yield, by your percent yield as a fraction. There's multiple ways to do this. I like this sort of cookie method where you express the number as what you actually need. Now, you can do this at the start or you can do it at the end. I could say that I really need to make 16 cookies, or I need to multiply my answer by 0.33. So, in the practical side, in the real world, how this would work is if you were given a problem like the following. A reaction normally produces an 85% yield of phosphoric acid. You need 45 grams of phosphoric acid. How many grams of P4 would you start with? Now, choices are twofold. You can either scale the products or you can scale the reactants. It doesn't matter. In this case, I'm just going to do it like I did the cookies. I know that if I start with 45 grams of H3PO4 as my target, I know, this is again my actual yield, that for every 85 grams of phosphoric acid, I need really to make one. I need to start with 100 grams because I'll lose 15 grams as waste. So rather than shooting for 45, what I need to shoot for is 52.9. I need to set up my calculation such that rather than aiming for 45, I need to aim for 52.9. And so is the theoretical yield that I'm shooting for, 52.9 grams of phosphoric acid. And then after that, let's convert our grams of phosphoric acid into moles of phosphoric acid, and then use the moles of phosphoric acid to figure out the moles of P4 that I need to start with, phosphorus, white phosphorus or red phosphorus, and then convert that into grams of P4 using the molecular weight. So if you set it up correctly and you run through the calculations correctly, you should get 16.7 grams of phosphorus is needed to obtain 45 grams, assuming that you will lose 15 or so % in the process. So we have to shoot for 52.9, but in reality we're only making 45. So a slightly more backwards procedure. if you run a reaction a bunch of times, and you can start to get a feeling for what the percent yield. I have a one chemical reaction that I run, I always get about a 50% yield. So I know that if I need to make 2 grams, I aim the calculation towards grading what should be 4 as my theoretical yield, but I only get out 2. So that's percent yield, and that's one of the real-world issues that you encounter when reactions do not produce as much material as you expect.